Okay, in section 5.3 for Advanced Algebra 2 Trig, it's the third day, and we are finding the three types of asymptotes and then learning how to graph a rational function by hand. So you make sure you want to have your graphing calculator for this lesson because we are going to use it at the end of this. Okay, so there's 5 boxes. The first box says, how do you find the vertical asymptotes for a rational function given r of x equals p of x over q of x? Well, finding a vertical asymptote is the same as finding the domain. So what we do is we set q of x equal to 0, and then we solve. So as an example, if I had the rational function r of x is equal to 1 over x plus 2 all squared, well, the 1 represents the p of x, and then the q of x is represented by the x plus 2 squared. So what we're going to do is we're going to set x plus 2 quantity squared equal to 0, and then we're going to solve. So that means that x plus 2 equals 0, so x must be negative 2. So my vertical asymptote is the line x equals negative 2. But we kind of already knew that because this is the tree trunk graph that's been moved over 2 units to the left, and that makes for the vertical asymptote. So this would be the same as the domain, right? So the domain of this thing will be all real numbers x such that x is not equal to negative 2. And it matters. Okay, so back to what we were talking about here. The second box of the day was learning how to find a horizontal asymptote. And before we can talk about a horizontal asymptote, we have to talk about this idea of a rational function being proper. So here's the idea. So if r of x, your rational function, is proper, and I'll explain what that means in just a second, then y equals 0, or the x-axis, whichever one you want to call it, they're the same thing, is the horizontal asymptote. I'll just say HA for horizontal asymptote. Okay? So what does it mean for a function to be proper? Because if it is proper, then y equals 0 is the horizontal asymptote. You don't even have to think about it, right? So proper means this. Proper. It means if the degree of p of x, which is the numerator of your rational function, is less than the degree of q of x. So that's what proper means. So if the degree on the numerator is smaller than the degree on the denominator, then your rational function is what's known as a proper rational function. Okay, and then we use that because we know we have a fact here that if we have a proper rational function, then y equals 0 is the guaranteed horizontal asymptote. So here's 2 examples I have for you. Take a look at this rational function, 3 over x plus 1. Okay, the degree on the numerator is like x to the 0. I can write that as x to the 0. So the degree on the numerator is a 0. The degree on the denominator is a 1. And since 0 is less than 1, that implies that r of x is proper. Okay? If r of x is proper, then y equals 0 is the horizontal asymptote. And there you go. Okay, so I brought up the calculator here, and I punched in the rational function 3 over x plus 1, represents my example there. And when I hit graph, you should see that the horizontal asymptote is y equals 0, or the x-axis right here. And you can see that there definitely is a horizontal asymptote there. Okay, on this one, my second example I have for you, right? The degree of the numerator is a 1. The degree of the denominator is a 2. So again, r of x is proper. So that means that y equals 0 is the horizontal asymptote. Okay, so that's pretty straightforward. So then the question you probably ask yourself is, okay, well, what happens if r of x is not proper, right? So as an example right here, take a look. I have r of x equals 3x plus 5 divided by 2x plus 7. Well, this is the p of x, of course, and then this is the q of x, right? And the degree on the top is a 1, and the degree on the denominator is also a 1. So now we know that the degree of P of x is actually equal to the degree of Q of x, right? So if the degrees are equal, then what we do is we say y equals 3/2 is the horizontal asymptote. So where did I get that from? So check it out. If the degrees are equal, you take the coefficients of the highest degree term, which in this case is a 3 on the numerator and a 2 on the denominator, and write that as a quotient, and y equals 3/2 is your horizontal asymptote. That's how you do it. Then we take the quotient of the highest degree terms. Okay, so if the degrees are equal, you take the quotient of the highest degree term. So in this case, we get 3/2. Here's another example, right? R of x is equal to 10x squared over 20x squared. Since both the degrees are a 2, they are equal, then I take the coefficient of 10 divided by 20, which is 1/2. So y equals 1/2 is guaranteed to be the horizontal asymptote, and I'll show you that with one of these here. So check this out. If I turn my calculator on, go to y equals, clear everything out. If I punch in 3x plus 5, y equals 3x plus 5, and then divided by the denominator of 2x plus 7, 2x plus 7, and hit graph, there's what I get. Notice that I have a horizontal asymptote that's been moved up. It's no longer the y-axis anymore. I mean, the x-axis is y equals 0. It's been moved up. So how far up has it gone? Well, it's gone up 3/2. So I can also graph the line y equals 3/2. And I'm going to make that line a little bit thicker so we can distinguish it. Push enter one time, hit the graph button, and there you can see it. The asymptote covers exactly where we're at. And even if you zoom in, you can see that the asymptote is still there at 3/2. Okay, so that's how you find a horizontal asymptote if it is proper or if it is not proper. Okay, next, how do you find an oblique asymptote for a rational function? Well, you have to start off by knowing this. You can only find an oblique asymptote for a rational function if the degree of P of x, which is your numerator, is greater than the degree of Q of x, which is your denominator, by exactly 1. If it's greater than 1, like if they have a difference of 2, then you get a parabolic asymptote, and we don't have to cover that in this class, but that's what you would get. Okay, so take a look at this example here, right? If I have r of x is x squared plus 2x plus 1 divided by x, notice that the degree of the top is 2, the degree of the bottom is a 1, and 2 is greater than 1 by exactly 1, right? The difference is 1. So therefore, we can find an oblique asymptote, and we're guaranteed to have one. So the question is how do we do it? So the way that we do it is we use long division. But it's actually much quicker than you think because you're only looking for y equals mx plus b. You're looking for the equation of a line. So here's what we're going to do. We'll just do this. We'll take x, and then we've got x squared plus 2x plus 1. So I have x squared plus 2x plus 1 divided by x, and we'll use our long division skills. X goes into x squared x times, so x times x is x squared. And again, I subtract here, gives me nothing. Bring down positive 2x. X goes into 2x 1/2 times. Because 1/2 times x is half of x. Is that right? Oh, I don't know what I was just doing right there. That's totally wrong. X goes into 2x 2 times. There we go. 2 times x gives you the 2x. So sorry about that. Just erase that last part there. And that gives you nothing. But here's the thing, right? We can stop once we get to here because all we're looking for is the equation of a line. So therefore, we now know that y equals x plus 2 is the oblique asymptote. And I'll just put OA. So let me show you that on the calculator to prove that we're not crazy here. Okay, turn it on. Go to y equals. Clear all this stuff out. Let's go to the top, and let's punch in our rational function. I'm going to use parentheses, keep everything together. Put x squared plus 2x plus 1, and then divided by x in this case. So I'm going to hit graph. Okay, I'm going to hit zoom 6 to get back to the original picture. So I have this graph that's sort of going off in a diagonal direction. There's definitely an oblique asymptote there, and I found the equation of it. It's going to be y equals x plus 2, and I'll prove that by going over here and saying y equals x plus 2, hit graph, and you can see that that asymptote goes right through the center of our graph, cuts it in half kind of, and moves on over. So if I zoom in, I can get kind of a better idea, sort of. You can see the asymptote as it moves up and down. So I found the oblique asymptote. The way you find an oblique asymptote is by long division, and you can only find one if the degree of the numerator is greater than the degree of the denominator by a factor of 1. Okay, last problem I'll sort of just walk you through. I left everything on here. So the fifth box of the day was learning how to graph a rational function by hand. And so here's the one that we're going to start with, okay? We're going to start with the rational function x plus 1 over x times x plus 4. So the first thing you want to do, step 1, is find the domain, okay? And the domain, of course, is all real numbers x such that x can't be 0 or negative 4. And we get that from looking at the denominator, setting it equal to 0, and solving. Next, we find the x-intercept. And the way you find the x-intercept is you set the numerator equal to 0 and you solve. So I set the numerator, which is x plus 1. I set x plus 1 equal to 0, and I solve, and I get a value of x is equal to negative 1. That is my x-intercept. Okay? Then my y-intercept, I substitute x equal to 0 into my entire rational function. So I have 0 plus 1 over 0 times 0 plus 4, which gives me, of course, 1 over 0, which I can never do. That's bad. I can't divide by 0, so that implies that there is no y-intercept at all. Okay, step 4 is to find the vertical asymptote, and you just look at number 1, basically, because we found the domain, because the vertical asymptote and the domain are the same thing. Okay, then we find the horizontal asymptote, and we take a look back over here, and we ask ourselves, okay, the degree of the top is 1 from right here. The degree on the bottom looks like 1, but you have to remember you're multiplying these two things, so x times an x gives you an x squared. So therefore, the degree on the top is 1, the degree on the bottom is 2. That would imply that we have a proper rational function, which means y equals 0 is a horizontal asymptote. And lastly, if you have a horizontal asymptote, you're not going to have an oblique asymptote because you can't divide that out, so there is none there. All right, great. Once you have all of that information, you got to start putting it on the graph. So I drew a graph here, and I started with the domain at 0 and negative 4. So at x equals 0, I have a red line, which represents a vertical asymptote here. And then at negative 4, I've got a red line, which represents another vertical asymptote. Then I put my x-intercept on the graph at x equals negative 1. There's no y-intercepts. The vertical asymptote was at 0 and negative 4. Horizontal asymptote is right here, the x-axis. And then finally, what I did was I took some test points. Right? I broke this up into a region. Like this is, I called this region 1 to the left of my asymptote. I called this region 2 to the right of the asymptote and to the left of the x-intercept. And then I tested a point in between negative 1 and the y-axis here. And then I have a test region called number 4, which I move everything to the right of y equals 0 there. So what I did was this. Okay, I brought up the calculator, and I plugged in this function into the calculator. So let me show you real quick. Okay, so I plugged into the calculator x plus 1 divided by x times x plus 4. And then what you can do is you can go to the table function. So it's hit second graph, and you get a table function going on here. So if I go over to negative 5, right? So when x is equal to negative 5, like in this region, notice I get a negative output. So that means that my graph has to be doing something on the bottom below the x-axis because I have a negative output. And it's bounded by a horizontal asymptote, and it's bounded by a vertical asymptote. So this is the only thing that it could really be doing. Okay, then I go to negative 3. Okay, at negative 3, notice I get a positive output. So therefore, my graph has to be doing something up here in the positive region, so above the x-axis, right? Let's go back, bring this back up. Now I need to test a point in between 0 and -1. So it's kind of hard for me to test that, right? So what I could do is I can go to second table setup, and I could go to change the independent variable to ask, go back to my table and ask what happens at -0.5, and I get a negative answer. So therefore I know that my graph starts positive, crosses the intercept, and then goes negative. So it has to come down, hit the x-intercept, and then go down to negative. And then I take any test point in the positive region over here, x. So how about x is equal to 3? Push enter. Notice I get a positive output. So therefore my graph has to be above the x-axis. And then, of course, once you do go to the graph, you see that you get this. Let me go zoom 6. You get this picture that looks exactly like our picture. We have the vertical asymptote at -4, vertical asymptote at 0, comes down, crosses, and goes below, and then goes down to the right. All right, so pause the video, go back and watch anything to make sure you understand, and take some time with number 5 especially. All right.